Hi everyone, welcome to MOSCAN. So in today's video, one PMOS M1 is given to us whose gate is connected to 0.9 volt voltage, whereas one terminal, let's consider it as drain terminal. So drain terminal is connected with 2 volt battery. So this potential will be always sitting at 2 volt, and at source there is one variable voltage source Vx is connected. About that, the information is given that the maximum of this Vx can go till 4 volt, and the threshold of this PMOS is given to us as equal to 0.8 volt, and we have to plot the graph of this IZ current with respect to time for this question. So if you look at this question, this looks to be a very easy question, but there are some important concepts involved in this question. We will study about those concepts in this video. So first of all, you must be knowing in any NMOS or PMOS, source terminal is defined by the applied potential. It is not always a fixed terminal. For example, in this PMOS, if you see, this is defined as a source node, so it will not be treated like a source terminal. What potential we are applying at this particular terminal, that will define whether it will behave as a source or not. So in PMOS terminal, the maximum potential will be tied to source. So if this particular node always sits at the highest potential, then it will be considered as source. If it becomes lesser than this potential, so this drain will become source and this will become drain. Similarly, in NMOS, the lowest potential is considered as source. So this is an important concept which will be used in this question. So let's start solving this question. So we have to plot Iz with respect to voltage here. So let's denote the positive x-axis as voltage and the positive y-axis as Iz. So first of all, the information which is given to us in this question is maximum Vx can go till 4 volt. So we will start solving from 4 volt onwards and we'll see what will happen. So let's consider this as 4 volt. Okay. Now, if we consider this node is sitting at 4 volt, in which region of operation this MOSFET will operate, that is important to understand. Then only we can draw the current characteristic. So if let's consider this node is at 4 volt, that means this node will be the source node for this PMOS because this is highest potential. So for a PMOS, if it has to be in the saturation region of operation, the condition which we know for PMOS is its VSD should be greater than or equal to VSG minus of VTH. This is the condition for PMOS, right? Now, if you consider the source potential as 4 volt and drain potential will be sitting at 2 volt, so and if we consider the gate potential is given to at 0.9 volt and source is at 4 volt, VTH mod if you are taking, so it will be 0.8 volt, so it will come 2 volt should be greater than or equal to 4 minus 1.7, that would be equal to 2.3. So 2 is not greater than 2.3, right? That means for 4 volt at this particular potential, this PMOS will work in linear mode of operation, because if you calculate VSG is always greater than VTH, right? VSG is coming 3.1, it is greater than VTH, that means PMOS is on, but it will behave in linear mode of operation. This is the first thing which we have got to know here. The second information is that, let's say if we start reducing this Vx voltage from 4 volt onward, it will start coming towards the 0. So what will happen if we reduce this potential? Let's say if it is sitting at 2.1 volt, Vx is sitting at 2.1 volt. So even in that condition also, if you calculate the same equation, if you apply here, we can write as 2.1 minus drain potential will be 2 volt should be greater than VSG. Vs is 2 volt and gate potential is 0.9, whereas threshold is 0.8. So still if you see, 0.1 should be greater than or equal to, it will come 0.4 if you calculate, and this is not true, right? So that means this PMOS will go in saturation only after that, once your Vx will become smaller than this drain potential. And at what particular potential this Vx will be, this PMOS will go in saturation, that I can tell you, it will go in saturation once your Vx value will be sitting at 1.7 volt, right? How it will sit in saturation at that particular voltage, I will come to that. But before that, one more important concept here is that once your Vx voltage will reach at exactly 2 volt, so what will happen in that condition? Although your PMOS is on, because if you see your VSG is 1.1 volt, that is higher than your VT, But VDS is 0. That means there would be no current in this PMOS. Although your VGS is greater than VDS, but VDS is 0, so no current would be there. So from 4 volt to 2 volt, our graph would be something like at 4 volt you will have certain current and at 2 volt it will become 0, right? This is what we have understood so far. How the graph will look like I will draw here, but for now we have understood this concept. Now as I mentioned, as soon as your Vx will reach at 1.7 volt, your PMOS will operate in saturation. How? Let me tell you that point also. So once your Vx will start becoming less than this 2 volt, that means this potential will become higher than this potential, right? So this particular potential which was earlier a drain potential will now become source and this will become drain. So this was an important concept which I was talking about early in the video that is now being implemented here. So let's say if your Vx is 1.7 volt, so what will happen? Let's calculate. VSD we need to calculate. So now source is this one, right? So VSD if you calculate 2 minus 1.7 it will come. It should be greater than or equal to VSG. Vs is 2 volt, G is 0.9 and your threshold is 0.8. So 0.3 should be greater than or equal to 0.3, right? If you calculate this. And this is true. 0.3 is equal to 0.3. That means at 1.7 volt, once Vx is coming lesser than 1.7 volt, then this MOS M1 will operate in saturation, otherwise it will be in linear. So this is one important concept here. Vx, if it is equal to or lesser than 1.7 volt, this PMOS will operate in saturation region. Else, if Vx is greater than 1.7 volt, it will be in linear mode of operation. So this was an important concept here. Now, so the third important point on x-axis is 1.7 volt, right? How now curve will look like? Let's talk about that. So at 4 volt, you will have certain amount of current flowing from this PMOS, right? And at 2 volt, it is becoming 0. And we know in linear mode of operation, MOSFET acts as a variable resistance. So if it is behaving as a resistance, that means the curve should be ohmic curve. So it will linearly decrease. So at 2 volt it's 0, but at 4 volt it will have certain amount of current. We don't know what will be the exact value of that current, but we can consider from 4 volt to 2 volt it will decrease a linear fashion. Let's call this as some current ID. Now, from 2 volt to 1.7 volt, still it will operate in linear mode of operation, right? And after 1.7 volt, it will go in saturation mode of operation. So what will happen? It will be increasing linearly and then it will be kind of saturated current. So like this, your current will look like. So this is the curve between ID, IZ and voltage. So from 4 volt it starts to flow and this magnitude will be definitely higher than ID. So I'm considering it as ID plus delta ID, that is higher than this ID current. So at 4 volt it will start having certain value, then from 4 volt to 2 volt it will start decreasing. At 2 volt it will be exactly 0. From 2 to 1.7 still the MOSFET will operate in linear, so it will continue to increase and after that it will be saturated current. And this current will be higher than the linear current. So this is how the curve will look like for IZ versus V. This was easy question, but two concepts was involved in this question. The first one is in which region of operation this MOSFET is operating and how the source and drains are getting swapped based on the potential at different terminal. And the second thing was about this curve. So I hope you might have learned something new from this video. If you found this video useful, please share with your friends. And if you haven't subscribed to our channel, please do subscribe.